Hey guys, this is going to be the 1.4 and 1.5 polynomial functions. And so we're just going to start talking about it and what characteristics that we can figure out just by given the equation of a given polynomial. So a polynomial function is any function representation equivalent to the analytical form. Um, this says here f of x is equals to a sub n x to the power of n plus every term that's degree less from that term, essentially, right? Until you get to your constant value, a sub 0. But if you want to read it out completely, you can read it out. But yeah. And so let's talk about where n is a positive integer, a sub I is a real number for each I from 1 to n, and a sub n is non-zero. So that's all the little subscripts that we have here. So in terms of determining a leading term, um, it's usually going to be what it says, the leading term, the number or term that's directly in front of the polynomial. I think a better way to put it is this way. I would say that it's the term with highest degree. That's a better definition in my head, so I don't mistake just looking at the first term because it's not always quite the case to be the leading term. So if I was to highlight, let's say I highlighted this first leading term in red. The leading term that they have above here as an example would be this portion right here. Instead, let me actually underline it. I think that'd be better. So that is my first term, right? That's the one with the highest degree because n, oops, sorry, n here is the highest degree because we'll end up subtracting every single time here until we have no degree at all. So that's why that's our first term. Now let's talk about where the degree is. This one should be fairly obvious, hopefully. So let's highlight this one in green. Again, that's just simply the degree that's associated here with the leading term. And then our leading coefficient, we'll highlight in blue. Let's do a bigger one. That's simply the coefficient that we have in front, a sub n. So let me write this out. Our leading term here should be a sub n x to the power of n. That's that chunk right there. The degree itself should just be n. And then our leading coefficient is just a sub n, right? That's just with, in general, what this should be. Let's work with actual examples so it's a little bit more obvious now. So let's see, it says find the leading coefficient and degree of the following polynomial functions. So same premise. The leading coefficient is the number associated with the highest degree. In this case, we have highest degree of 4. Thus, our leading coefficient is simply the number in front, so 3. And then if I want to talk about that degree, well, we can see it to be 4 as well. So there's our answers for that. And here's where my definition of leading coefficient is important, right? You can see the order of this. It's not from highest degree to lowest. And so if you were to claim that 12 was your leading coefficient, that'd be wrong. Again, it's the number, or sorry, the coefficient that's associated with the term with the highest degree. So in this case, it's going to be negative 7. So I'll say negative 7 is my leading coefficient with a degree of 3. And then now, let's do this last one. I got g of x is equals to 4. Although there's not any other terms, nor is there any degrees at all, I can still figure out this information. So leading coefficient is just a number that's currently present, just 4. And then the degree is, well, there is no variable. So there's not really necessarily a degree to base it off of. So in this case, there is no degree. So I'll say none. Or a better way to say that is probably 0, right? We have 0 degree. That's also fine. Both means the same thing, but we'll just write 0 though. All right, buddy. Are you trying to leave? Let's see. All right, now let's talk about extrema. Right, so extrema is definitely a vocab word you have heard before, but let's talk about it in case you haven't. So it says the extrema of a graph are the maximum and minimum of a function There are two types of this, as we can see here below, right? There's either relative extrema, or is there going to be absolute extrema? So let's take a moment to read each one. So let's see here, let's read together. Relative extrema, or perhaps local extrema, is a polynomial has a relative minimum or relative maximum where it switches between decreasing and increasing, or at an endpoint if the polynomial has a restricted domain, right? That's going to be your relative extrema. So the biggest takeaway here is that the moment it switches from increasing to decreasing, that's how you tell whether or not you have relative extrema. So if I was to point that out on this graph right here, I would point it out at specifically at perhaps 3 locations, right here, here, and here. And so at each of those spots right there, that's where my actual graph is switching from increasing to decreasing. Now let's talk about absolute extrema, or perhaps global extrema. Cat has never done this. Do you guys see him? You good, bro? I think it's good. Hopefully it doesn't fall. All right. It says of all local extrema, or sorry, local maxima, the greatest is called the absolute maximum. The least of all local minimum, or sorry, minima, is called the absolute minimum. So it's basically just the highest or the lowest point of my graph if I have it. So for example here, if I was to find the absolute extrema, I would say that the highest point is definitely here. And if I was to indicate the lowest point on this graph, the absolute minimum, some of us might claim that this right here is my lowest point in the graph. And I'll just be careful and just make sure that we look at the whole graph and see that's actually, we're being misled just a little bit. If we notice here on the right hand side, there's an arrow that still continues our graph forever in the downwards direction towards the right. And so more importantly, it's still going down forever. So there's not exactly a lowest point that my graph can be at. So inherently, there is no absolute minimum, but there is an absolute maximum. And so with that being said, I think I've answered these kind of naturally here by accident. So over here, I have a few local minimums, right? I have one at x equals -4, and then at 0. And then as far as my local maximums, I have them at x equals -2 and 3. And if I go and fill this out for my absolute minimum, again, we shouldn't have one. We should say none. Due to the fact that this arrow here goes down forever, which means I don't have a smallest place that I can rest at. But there is a maximum, the highest point of my graph, located at x equals 3. Hopefully this idea is straightforward. Now let's move on to the next part and talk about some small facts about polynomials. Okay, it says between two real zeros of a polynomial, there must be at least one max. That is the general rule here for that. One max or one minimum. So if you have two real zeros of a polynomial, there must be at least one of each. Either or, not both, not always. And so the reason why that's true is, well, because if I was to draw a graph and label any two random zeros, my graph would have to look variously to make this work, either like this or some crazy combination like this. Doesn't really matter, as it goes through those zeros for sure. And you can notice whatever I draw, even like something so simple here, something like that, that has to have a maximum. And if I drew it the other way, going through those two zeros that I figuratively drew, then I have a minimum, right? Regardless, no matter what variation that I draw, you'll end up having at least one maximum or minimum. That's inherently true. Now let's talk about the second part here. This part is talking about polynomials of even degree. Polynomials of even degree must either have an absolute max or absolute minimum. Either or, right? And so when we think about even degree functions, right, we think about the NBA reporting in the same direction. But we'll get into that later in the notes here. me just make sure my mic is still working. Yes, it is. All right. Now let's talk about points of inflection. Now we kind of talked about this in the previous units, or I might have just said it loosely, while not having an official definition, but I think we should have it now. So it says that a point of inflection occurs when the function changes from concave up to concave down, or from concave down to concave up. So either or. I should highlight so you read with me. At a point of inflection, the rate of change of a function changes from increasing to decreasing, or from decreasing to increasing. Right? So at a point of inflection, the rate of change of a function changes from increasing to decreasing, or from decreasing to increasing. So really all that's saying is restating the statement that we just read here, but with the literal definition of using rate of change, right? So let's take a look at what some of the problems we have that's concerning this graph here. So it says the graph of g of x is shown in the figure above. Use the graph of g to answer the following. Find any values of x where g has a point of inflection. So I'm looking for where the slope is changing from increasing to decreasing. Some of it's quite obvious depending on the graph that's given to you. Sometimes they're not, but in this case, I think I can see it, right? The moment we go from concave up to concave down, for example, right? So I notice here, I start off, I am currently increasing in slope into right about here. That's where I would probably transition from an increasing slope into a decreasing slope. Because as you can see now, moving forward, I have something that's considered to be concave down, the thing I'm shading in red. And I think right about there again, since this is somewhat symmetrical or exactly symmetrical, the point of inflection should happen again right here, where we go from concave down back to concave up, meaning our slope is now increasing again, right? And so with that being said, I can find those exact x values that I have colored in red there. So I'll say x is equals to either -1 or 1. Those two spots right there are our point of inflections. Now it says for each of the following intervals, determine if the rate of change of g is increasing or decreasing. Explain your reasoning for each answer using features of the graph. So as long as you're kind of comfortable with 1.1 through 1.3, there should be no problem. This kind of just kind of review as to whether or not these intervals represent an increasing slope or a decreasing slope. So whether or not it's going to be concave up or concave down is what they're saying. So let's observe the first interval. They're saying from 3 to 4. Let's see what happens at 3 to 4. So I might signify this of what I'm looking at with a blue marker here. So from, where's 3? 3 is here, and I should stop at 4. So from 3 to 4, I can clearly see that my slope is currently increasing, right? And in general, what I have highlighted in this orange here is we signified earlier to be concave up. So inherently, my slope must be increasing. So I can claim at 3 to 4 that the average rate of change, or I could just say rate of change, the ROC, is increasing. Now let's observe -4 to 3. Again, I'm going to also still continue to use blue for this. So let's mark where -4 is. -4 is here. And I need to go all the way to, what is it, 3? And if I was to observe in between the blue arrows that I drew, right, we're a mix of both, right? It starts off as concave up, right? It starts off as concave up, with this stuff here, into concave down, back to concave up. So inherently, this blue section is kind of unclear what they want us to answer here, right? This is determine whether or not it's increasing or decreasing. Well, technically, it's both that's happening, right? It varies. And so I would claim that both is occurring in this interval. And let's be more specific with the answer. I wouldn't want to claim that the entire -43 where both it is happening. I would say maybe it just specify that. I would say from -4 to about -1 is my increasing. as well as the 1 to 4. 1 to 4. So I'll say this is my increasing average rate of change. And then for the decreasing section, I'll also specify it to be in that red section that I have highlighted from -1 to 1. Just so I can be more concise with my wording. That's all. And what I'm claiming to be increasing or decreasing. All right. Now let's do part C. Now that's saying from -1 to 1. Let's see where that is. So let's adjust our blue arrows. From -1 to 1 is right here to here. And so that's what I have highlighted in red, which we already claimed to be concave down. And by definition of concave down, that area must be a decreasing rate of change. So I would just claim that this one is decreasing. And then one last interval, 1 to 2. So let's see, 1 to 2. Let's adjust our arrows one more time. From 1 to 2, it appears to be this specific section here. And so it seems like in this area that I have in blue, or highlighted in orange, is considered to be concave up. Thus, my slope must be increasing at that section, or at that interval. So I would claim in this interval, we are increasing. The function g is increasing there. Or, sorry, the rate of change of function g is increasing there. That's better. All right, let's move on to even and odd functions. All right, an even function specifically is symmetric over the x-axis, and then an odd function is symmetric over the origin. And so we're going to take some time to observe this truth here, right? So in this first graph, we may not feel like this is reflected or sorry, symmetric over the x-axis, but yet it is, right? A lot of us think that, oh, that just means like I need to take this specific section here and then it should be perfectly mirrored across the x-axis. Not in this case, right? This is not the classic symmetry that we see, right? So again, it's being symmetric over the x-axis. Let's observe it by definition that's provided to us here. Right, this will be a lot easier to see. If anything, I like to imagine that it's really over the y-axis as opposed to the x-axis, but that's just me. Um, but yeah, let's take a look. So I would test a value and see if it's true. So let's see if I was to test a negative x value, and we can pick any here. Let's say I picked -3. At -3, I have a specific output right here associated with it of 2. So I know when I plug in -3, so f of -3 is equals to 2. Now they're claiming in this definition that it's equals to f of x, which means if I was to plug in f of +3, I should get the same result. Then we can check if that's true. So if I plug in +3 here, what I have highlighted on the right-hand side, I also get a return of 2. So it seems like our definition is correct, right? F of 3 is equals to 2. Now that I'm really thinking it over, I don't think it's meant to say x-axis here, right? I think it's really meant to say y-axis. Um, the more I'm thinking about it. If I'm wrong, I'll correct it, but for right now, I think that's right. I'm looking at a key here, and I don't think um, that's quite the right assumption. But nonetheless, hopefully that makes sense. All right, let's take a look at the odd function now, right? And how it's symmetric over the origin. And so let's see, we're given an example of g of x is equals to x cubed minus 9x. And so to tell if it's symmetric over the origin, we have this statement, this definition here, or math definition. This must be true. So if I plug in a negative x value, that's the same thing as having a negative affect the general output of a normal positive x value. So let's just test that to make sure we understand what I just said. So let's find a negative x value. Doesn't really matter. I will pick, let's say, -2. The associated output value at -2 is +2. So it seems like f of -2 is equals to 2. So that's what we're claiming for this left-hand side here. What should happen on the right-hand side, hopefully, is that we get -2 somehow as the output. So as long as I test the positive version now of f of 2, let's highlight where that is. That's right here. The associated y output on our graph is down here at -2. So I got f of 2 is equals to -2. That's exactly what we wanted, right? That's exactly the situation or definition that they provided. And that's true for all points of this graph. And so if you were to test it, for every single point in this graph, the statement will end up being true. That's what makes this an odd function. All right? All right, let's go and try out a few problems here to determine whether or not these functions are either even, odd, or neither. And so that's basically just me testing out uh, the rules we had earlier. And for me, I'm kind of noticing that, well, this inherently is an even degree function. Let me just try out the even definition because more than likely it will work. Not always does that trick work, but it works here for this problem. So that definition again, I'll write in red. So h of x is equals to h of -x, right? That's the claim for an even function. So let's plug -x in and see if we get the same function in return. So I'll plug in h of -x. That's equals to 2 times -x to the power of 4 minus a -x squared plus 5. At this point, I'll just simplify. This ends up leaving me 2x to the power of 4 minus x squared plus 5. And so the resulting function is exactly the same one that we had at the beginning. So this statement that we claim to be an even function is true. So I can claim that this function here is an even function. All right, the mic is still going. Let's hope it doesn't shut off anytime soon. All right, here we go. We have b of x equals to 2x to the power 5 minus 3x. And so I already kind of noticed that it's an odd degree function. So more than likely it's going to be an odd function. So we can try out that odd definition. Let's rewrite it again. In this case, it's going to be b of, what is it? I already forgot. B of, negative x is equals to negative b of x. And we'll test if that's true, meaning I get this function to become negative basically if I plug in -x. So all the signs will flip. So if that happens, I know that this is an odd function. So let's try that out. I'm going to plug in -x now into the function. I get 2 times -x to the power of 5 minus 3 to the -x. If I simplify this term here, my leading term, then a -x to the power of 5 retains its negative. So overall, this becomes -2x to the power of 5 plus 3x. And so when you compare our final answer to the original function, you can see that it's simply just the original function with the signs flipped. So we have confirmed that this is an odd function. So b of x is an odd function. All right, let's do the last one and see what happens here. And so again, the idea of saying that, oh, just because it's an odd degree function doesn't automatically make it an odd function. Those are two different classifications, right? It is for sure odd degree, but let's test the odd definition and see if it actually ends up being an odd function. So that means I'm plugging in a -x and seeing what I get in return. Hopefully I get the negative version in return. So I have -x cubed plus 3 times -x minus 1. If I simplify this, I get, what is that? -x cubed minus 3x minus 1. And it was really close to being an odd function, right? If you look, right, this sign changed from positive to negative. This one went from positive to negative. But this one, not so much, right? The whole function must flip signs for it to be an odd function. So since it's not odd, we can test if it's now even. And we really don't have to do much more work, right? Let's just compare what I have right now to the original function, right? To be an even function, what we get in return after plugging in a negative x is that these would have to be the same. And obviously, they are definitely not the same, right? They have different signs for the first two terms. So we can claim for this particular function that it's going to be neither, right? It is neither odd or even, right? So basically, the test to see whether or not it's even or odd is just by plugging in negative x to see what you get back. So do you get the same function back after plugging in negative x? Then you have an even function. If you plug in negative x and you get the function but with flip signs, then you have an odd function. And then you have like a mix match of that where it's not entirely true for either case, then you say it's neither. All right, my mic likes to turn off very randomly. Hopefully that pause wasn't that awkward. Let's move on to the next part here. All right. So we want to be able to look at these graphs here and determine whether or not they are even or odd functions. Some of us might be able to see it very inherently, just graphically. I'll just say that for sure that this one is, yeah, it's an odd function, right? It is symmetric over the origin, right? I can take this point here and really apply that definition if you want to, and say that, well, at negative, let's be more specific, at negative 1, right, I get an output of 3. If I plug in positive 1, I better get negative 3, which I do, right? That matches our definition of f of negative x is equals to negative f of x. And so, oh, you guys can't see that, right? So that matches my definition there, but visually for me, I can see that this is an odd function after experience. But if you want to do by definition, it's true for all points here. Now we check this next one. This one is inherently neither, right? The reason why I say that is, well, if I try to compare this specific portion, let me highlight it for you, and reflect it over the origin, it doesn't quite do that perfectly, right? I have a parabola here that is somewhat, you can see that it's shifted in a way that even if I did flip it, it would not be symmetrical over that. Nor will it be symmetrical over the y-axis, right? If I try to flip it, it should be evenly on the other side over here, but it doesn't really quite do that. It's not the same distance, right? And if I even did the even definition, meaning if I plug in, let's say a nice point, negative 1, I get this point here. So if I plug in positive 1, I should also get 1 in return, which I don't. So it's not an even function, right? What else do we have? Oh, we still have a little bit more. Now we have end behavior. End behavior of a function describes how a function, let's see, behaves. Oops, that's a marker. I want to say behaves as it moves infinitely to the right and left. In other words, the end behavior is what happens to the values of y as x increases or decreases without bound. And so here's a notation that we have here, right? It's called limit notation for end behavior. So it says left end behavior, limit of the f of x, right? The limit of the function f as x approaches, right? As x approaches negative infinity. So let's say that again. I have the limit of the function f of x, or limit of f of x, as x approaches negative infinity. And so if we approach it from negative infinity, that's the left-hand side of my graph. And then the right-hand side is simply this notation here, the limit of f of x as x approaches infinity. Hold on, I need to pause for a second. I'll be back. All right, I'm back. Sorry, I had to do a quick text. Let's see where we left off. And so I shouldn't really skip to left to right like that so quickly, but for left end behavior, right, it's as x values decrease without bound, the y values of f of x are doing this essentially, right? That's the super mathematical way to say that. And this is a super mathematical way to say right end behavior, right? As x values increase without bound, the y values of f of x are doing what, right? So let's see how we kind of say this now for a few graphs. So if I was to say the left behavior verbally, I can kind of follow the general guideline here. That's a very mathematical way to say that. Or something you may have heard in the past is, well, we've done end behavior notation like this. If you recall, we're not going to do this anymore, but the way we can verbally say it is essentially saying this. As x approaches negative infinity, y is approaching what, right? We've done this notation before, but as far as how we say it verbally, that's how I'm going to say it, right? As opposed to this super, uh, I guess, math heavy way to say it, right? It's very just math jargon heavy. This is more layman's terms way to kind of go about saying it. So I would say as x approaches negative infinity, this left hand side here, my y is going up to positive infinity, right? That's how I would say that. And then as far as the left behavior limit statement, let's be very specific now, right? We're talking about the limit of our function f of x as x approaches negative infinity. So we're talking about the left-hand side. What is this equals to? Well, as we do that, we are approaching positive infinity, right? That's how we write that. That's how we write that. So we went from the old notation that I wrote here a moment ago, I should have left it, into this newer, cooler notation, which is going to be very, very useful to understand in calculus. So make sure you use this, right? Now let's talk about right end behavior, right? So we're talking about the limit, or sorry, this is verbal, right? Uh, Let me write it down what I'm going to say. As x approaches positive infinity, as I go to the right, y is approaching negative infinity, right? That's verbally what I'm going to say. Or you could say it as x values increase without bound, the y values of f of x is decreasing, right? That's how they want you to say it in these notes. But I think both are fine. Both are fine. So now let's actually write the right behavior limit statement, right, using limit notation. So limits, or the limit of f of x, as x approaches positive infinity, as I go towards the right, is all equals to, well, as I go to the right on this graph, it's going down, so towards negative infinity. All right. Now we have one more problem. If you want to pause here and give it a shot yourself before I go through it, you can. If not, I'm just going to go do it. So pause now. If not, here we go. All right, left behavior verbal, right? Verbally, I will say it the math way here and say that as we approach left, right, as x values decrease without bound, the y values in this case are going up, right? So as x values decrease without bound, this is what it means as it goes on forever, the y values are increasing to infinity or approaching infinity. But let's write this with limit notation. So as the limit of, let's change the function's name since we used f of x already. Um, let's use g of x. The limit of g of x as x approaches negative infinity is equals to positive infinity. Then right behavior, verbal, as x increases without bound, so does the y value towards positive infinity. And so I'll say that the right behavior limit statement, right? I'll say the limit of g of x as x approaches positive infinity, that's equals to positive infinity. All right, that is about it as far as end behavior and general polynomials. Um, if you have any questions for me, shoot me an email or ask me in class. Right. Best of luck. Y'all take care. I want to go to bed now. Bye.